Thanks everyone for coming. As you probably have noticed, now all the seminars are at 4 p.m. of Wednesday. We had a few weeks where we were shifting from 2 to 3 to 4. And today we have another guest, and Martin is basically a co-author of me and Armando, and yeah, he's gonna shows us about his results from his paper Incompatibility in Restricted Operational Theories, Connecting Contextuality and Steering. So thank you, Martin, for coming, and please go ahead.
Thank you very much for the introduction. So I would like to somehow say a little bit more that what I mainly do, apart from working with Ale, is that I work on quantum foundations. So I work on quite abstract stuff usually because I find it interesting, and that's what I call having a good time. And that's also why there's this operational theories in the title. It somehow means that all of the calculations that I'll show you today in the original paper, I wrote them down not in quantum theory, but in some kind of generic theory or in a generic class of theories that's broad enough to include anything you can imagine in one afternoon. And and while it's possible to be more general than that, it's a pretty big class of theories. But despite that, to somehow keep the level of the talk on a reasonable level, I will show you all of the calculations only in quantum theory. And if you're interested in the more general stuff, feel free to either read the paper or send me an email and we can discuss this and so on. So that's why there's this operational theories in the title, but I will not mention them in the talk. So what's the point of this talk is that somehow I realized that there's several ways to define what classicality means in this kind of restricted scenarios where we have on some preparations and some measurements. And I somehow wanted to make inner peace with all of these possible descriptions. So I investigated like how they work together and which are connected to the other ones. And the result is this paper. So while this will not be somehow extensive list of equivalences between all possible hidden variable models, this will be a sketch of what one can do about contextuality, steering, and incompatibility. But before that, I should introduce the scenarios that are going to be in questions. So, and even before that, since I know that this is for a computer science group, I want to do a short recap of how I use quantum theory, because I know that many people in computer science, they only think about vectors in Hilbert space and projective measurements, but we have to generalize this. So instead of state vectors, I will use density matrices, which are positive semi-definite operators, such that their trace is equal to 1. So if you have a state vector, for example, something like a cat0, then the corresponding density matrix would be the projector, so something like catbra 0, 0. And then general density matrix is just a convex combination of these projectors. So these are going to be what I call states. These represent states of your system. So for example, if you have some kind of computation in quantum computer, at every point in time, you can write down the vector or density matrix for your system, and this is the state. And then there's the measurements. So this is what we apply at the end of the computation when we want to read out the classical values. And the measurements are going to be represented by POVMs, which are tuples or lists of positive semi-definite operators, which sum up to identity. And then we compute probabilities using the Born rule. So we just take a density matrix, you just take a projector, and you trace this against each other. And this gives you a probability. Now, this condition that the measurement, or also called POVM, sums up to the unit operator, just somehow translates to the fact that your probabilities sum up to 1, because probabilities should sum up to 1. And this condition that the POVMs are positive semi-definite just translate to the fact that the probabilities are positive numbers, because we should not have observable negative probabilities. So what would be the POVM the easy formalism of on the Hilbert spaces, well, this would be something like projectors on the eigenvalues of your Hamiltonian, or this would be projectors onto the computational basis. And then if you would write down your density matrix as a projector, your POVM as projectors, and you would compute this would exactly give you the square of the inner product, which is the probability that we compute using vectors on the Hilbert space. So this formalism is somehow slightly more general, but it's essentially still the thing that you know. And whenever you get lost, please imagine that the density matrix is just a projector representing the state, and POVM is just a projector representing the measurement. And it would be mostly correct. Or also, if you ever get lost, please feel free to ask me and I will clarify anything. Good. So now that we're all on the same page with quantum theory, we can start discussing these restricted scenarios. And there's two possibilities how restricted scenarios can happen. Some people say that they happen because in principle, there can be something in nature which we cannot observe or cannot observe exactly. So then we have to work with some restrictions. But also, I like the more pragmatic approach, saying that in principle, we can measure any measurement that quantum theory allows us, but in practice, we don't have to have this in the lab. And the devices to measure this could be expensive. And sometimes it's like, you cannot always come to your boss and say like, hey boss, I need another 5 million euros to implement this extra measurement. At some point, your boss will tell you like, no, you already have 5 measurements, make do with those, okay? So some kind of restrictions can arise either from a foundational perspective or from a purely practical perspective. But anyways, most of what we do actually can be captured by these restricted scenarios, and mathematically they all work the same. So I don't have to tell you where the restrictions come from. They're just there. So what happens? In a restricted scenario, we have only some preparable states, rho x, where x is the label of the state. Now, this x can run over continuously many values. So this does not have to be finitely many states, but it's good to imagine that it's not all possible density matrices, but it's only some subset of them. And I will use K to denote the set of all preparable states. Using some kind of operational thinking, we can assume that K is convex, because if you can prepare two states, then you can also randomize the preparation and you somehow prepare the convex combination. So this is the set of preparable states that we can prepare. It doesn't have to be all states, but this is the best we can do. The same story with measurements. We have some POVMs MA, and we will denote the set of preparable or measurable measurements by E. So then again, this does not have to be all POVMs. This can be some POVMs. The restrictions can somehow be tricky because sometimes you can do all projective measurements, but not all POVMs. And then this is somehow more complicated. But in principle, all of this can be described and all of this should be taken into account. And then we can start computing these accessible probabilities, like probability of observing outcome A given preparation X using the Born rule. So as you can see, one thing is missing here, and that's channels or some unitary transformations or gates. In principle, when I say channel, you can think of a gate in a quantum computer. And this is because this description somehow comes from is more oriented towards cryptography, I would say, or somehow it's more cryptography enabled, maybe. And there we don't really use channels as much, but in principle, one could also include something like channels in this to describe quantum computation, but I have never seen this done in a really satisfying way. Although there are some sketches of how to do this by Speckens, it was never really like heavily investigated. There's no good enough results that could tell you about this, except for telling you the definitions. So for this, so in this sense, we don't have any channels. We have only like preparations and measurements, but this is still good enough because, for example, if you think about the protocol like BB84, in BB84, Alice prepares something and Bob measures it. Like there's no channel. We assume that the transmission channel is only identity. So somehow in some of these protocols, we don't need channels, and this is going to be about those ones. So the main question now is, when can we find a classical description for what we are doing? And this is an interesting question because in principle, if we have a restricted scenario, we want to have some kind of conditions for when we can do something non-classical with the restricted scenario. Because obviously, if you restrict too much, you somehow can do only classical stuff. And at that point, you cannot have any quantum advantage for whatever you're doing. An easy example is that, for example, we can have no restriction on states, which means that you can prepare all states, all density matrices, but you can perform only single projective measurement. In this case, for example, this scenario is classical in the sense that you cannot perform quantum key distribution with BB84 protocol because BB84 requires Bob to measure two different measurements. And if you have just one different measurement, then there is a perfect eavesdropping strategy for whatever Bob can do. So somehow we want to capture this. We want to capture the classicality of the restricted scenario. But as we will see, this is not so easy because there's many different ways we can capture this. So one of the obvious ways is that here Bob has a single projective measurement, but even if Bob would have more measurements, then if all of these measurements would be commutative, so all of the POV, all of the projectors would commute with each other, this would essentially be just one big measurement, and it would still somehow boil down to this one measurement thing. And this is something what we call compatibility or joint measurability. And so we see that, for example, some level of classicality should be given by joint measurability. So let us, or incompatibility. So let us review this concept first. So the idea is as follows. We have two measurements given by POVMs MA and NB. And we say that they are compatible if there is some kind of POVM GAB, such that if we sum over B, we get MA, and if we sum over A, we get NB. So this generalizes commutativity of observables that we know from the standard quantum theory, as in, for example, if your Hamiltonian commutes with angular momentum, then this is the generalization of that line of thinking. But, and this is quite straightforward to do in unrestricted quantum theory. But now when we introduce restrictions, the question is like, what operators should GAB be? Like, what should they be? Because on one hand, you can say that, okay, they should be a POVM that we can in principle measure. But on the other hand, you can say like, okay, but they maybe do not have to be a well-defined POVM. They have to be only positive on the states that we have. So, in other words, to explain these formulas better, I use this picture. So what we do there is that we basically summing over one index is summing over the columns, and summing over the other index is summing over the rows. So that's just a graphical representation of these two equations. So now to the restricted theory. So in the restricted theory, we can define two different concepts of compatibility or joint measurability, because one of them is if the joint measurement is a valid POVM, so all of the operators are positive semi-definite. And this, for some operational reasons, I call E-compatibility, while the other possible definition is that the joint measurement is only positive on the states that you can prepare. And this I call EK compatibility. These names, E-compatibility and EK compatibility, they come from operational theories. If at any point you forget which one is which, don't hesitate to ask me. Like, I have even written down which one is which on a piece of paper so I don't forget. So now I would like, well, this notion of E-compatibility is straightforward because this is a joint measurement that you can perform. People can object to EK compatibility, as in, why would you want to do this? Because then the joint measurement is not a valid POVM. It only gives positive probabilities on the preparable states that you can prepare. And this is because this somehow means that, okay, your two measurements are not jointly measurable, but the preparations, the states that you can prepare, they do not witness the incompatibility. And this is the main idea here, is that while the measurements are incompatible, you cannot harness the power of the incompatibility with the preparations you have. And this is important because even if we have incompatible measurements, we have to also, this shows us that we also have to have the preparations that harness the power of the incompatibility, you know, and this is not always trivial. So that's why there's two levels of incompatibility that we can define.
I have already a question.
Yes,
but So these GAB, you call them operators, but because it's something that we can realistically imagine using as a measurement operator, or it's something disconnected from this idea of measuring. So these are not POVMs, no? You said.
So in the first option, they are POVMs. In the second option, they can have negative eigenvalues, but you cannot observe the negativity.
But we are not requiring completeness, like they sum to one, to the identity.
You get this for free, just because if you sum here over A, then you get here identity, and here you get sum over AB.
Okay.
So you usually get this normalization for free. Even when you code if you would code this as SDPs, you don't have to require normalization. It's already there.
Mm-hmm.
Yeah, sorry. Yeah, I think because M and N are already normalized, then the normalization of G's follows. It's just about the positivity, or whether you can witness the possible negativity with the states, if I understand.
Yes, exactly.
Okay.
Okay, thank you.
All right. So this is incompatibility, but while this tells us something about the measurement, this tells us nothing about the states, or only tells us something about the states with respect to the measurements. So we have to go even further, and we have to define other concepts of classicality in the restricted scenarios. And for this, we have to introduce hidden variable models and essentially contextuality. So for this, we somehow need to think more about how the experiment happens. And this is a simplified, or this is a simple enough image that we can use, is that we have some kind of input data. So this tells us in the morning what we should do. And we use a preparation to prepare a density matrix based on the input data. But here, the important thing is that the input data is classical. This is classical description of what you can do. This is like a recipe, like a cookbook recipe. And the preparation gives you a quantum state. And then after preparing a quantum state, we use some kind of measurement M to obtain the output data, which is again a classical data saying that what we measure, the probability distribution. And here the main idea is that, okay, this is in principle all the experiments that we're discussing, because we can then say that the preparations are restricted, the measurements are restricted. And now we want to formulate some kind of hidden variable model as a classical description for this experiment. And the first thing, the most naive one, is something like this. Now, don't be afraid about the diagram. It's not that scary. And also, if there are some category theory people, these double arrows, they're not really natural transformations, but maybe they can be made into such. But they're arrows between arrows. So here the idea is that in the left column, we still have our original experiment. And this S lambda, this is the hidden variable model. This is a classical theory which we want to use to describe our experiment. Instead of performing the quantum experiment, we want to somehow describe it as a classical experiment on this hidden variable lambda. So what we can do is that based on the preparation P, we can map this to a preparation of the hidden variable. So instead of preparing a quantum density matrix, we prepare a classical hidden variable. So we somehow write it down. And then instead of performing quantum measurement M, we somehow from this get this mu M, which is a measurement on the hidden variable, which is just some kind of filtering of the hidden variables or binning. And from that, we can get the output data. And so then we say that the experiment has this form of hidden variable model if this probability that we get from the experiment can be decomposed into this sum, where we sum over all possible values of the hidden variable. The second thing here is the probability of preparing hidden variable lambda given the preparation P and the input data X. And the second one is what we call response function. This is how you compute probabilities from the hidden variable. Now, while this might seem like a good idea, the existence of this hidden variable model is completely trivial because this hidden variable model always exists. Because here you must, you see that you not only exactly know the input data, but you also have exactly know which preparation is going to happen. So in principle, instead of preparing the density matrix, you can write it down on a piece of paper. You can exactly write down what density matrix would be prepared. And since you also have exact information about what measurement will be measured, you can simply write down the corresponding POBM and you can compute the traces by hand and do this. And by doing this, you are constructing a hidden variable model. Not very efficient one, but nevertheless, it would be a hidden variable model for the experiment, and it would give you the same probabilities because the theoretical prediction must somehow coincide with the measurement outcome. So
in this case, which are the hidden variables?
The hidden variables are the lambdas here, living in this S lambda.
But can I think this as a classical computer simulating
Yes. You can think of S lambda as the hard drive of the classical computer. This eta p is sometimes something like pushing stuff to the hard drive, and this mu m is something like reading data.
Okay.
Yes.
So my whole simulation is what is called hidden variable.
Yes.
I see.
Yes.
Thank you.
But this does not imply that your simulation is efficient. So
yeah, of course. I thought, yeah, clearly.
Okay. But okay, so while computationally it would be interesting to look at something like efficient simulations, here we want to go another way, and we want to think about what if we wouldn't have access to the exact preparation and input data, but we would only have quantum access to the density matrix. So from this, we get something like preparation non-contextual hidden variable models. And the main idea is that we don't know the classical input data, and we don't know what preparation was used. We can only access the density matrix that was prepared. So this means that we have quantum access to preparation because we have only access to the quantum density matrix. And when I say quantum, I really mean that somebody gives you a particle and says like, hey, this is what I prepared. You know, so like really a quantum state. And then what we can see is that the corresponding hidden variable model would be that you have to somehow map the density matrix into the hidden variable, and then somehow from this compute the data. Which means that, okay, now where we had here before the probability over a hidden variable computed somehow from the preparation and input data, now we have to compute this from the density matrix. And since we have to assume that this operationally, we have to assume that this is a linear function, so it must be of this form. But now the trick is that these n lambdas, this does not have to be a POBM. This only has to be positive on the preferable states. This is because somehow, while we can prepare only some states, we in principle don't know whether the other states exist. Although quantum theory tells us so, we have no experimental evidence of the other states existing in this experiment, so we somehow cannot assume that they exist. And for this reason, this n lambda could in principle have negative eigenvalues. Or the other way to look at this is that the same as we had in the EK compatibility before, that we somehow allow for negative eigenvalues, but this trace expression must be always positive, because we somehow want to test this thing that we want to see whether the states can actually witness the non-classicality that's going on there. So this is preparation non-contextual hidden variable models. Now, okay, so here we had only quantum access to preparations. Now we can use the dual idea that, okay, we have only quantum access to measurement. So somehow we know exactly how we know exactly the input data, we know exactly the preparation, but somehow we want to perform the measurements within quantum theory. So the measurement must be quantum and cannot be described by classically. And this is where we get measurement non-contextual hidden variable model, which is something like Cohen-Specker non-contextuality. It's something like, so if you're an expert on Cohen-Specker contextuality, I know that there's other assumptions and other stuff, but in principle, this is something like the main idea, or one of the ideas going on there. And the idea is that, okay, we somehow compute the distribution of the hidden variable corresponding to the preparation. And now we have to map this to this set SE, which did not appear up to now. But this is something like the set of preparations which can be measured by the measurements we have available. Because as before, when we allowed the measurements with negative eigenvalues, just because we had no preparations to witness this, here we have to allow for slightly more preparations because we have no measurements to witness that these are not valid preparations. So this is this SE, you can somehow think of it as being the same as K, or maybe like slightly bigger set. But so what happens here is that we, instead of replacing the second probability to be computed classically, we replace the first one to be computed classically. And here we assume that, okay, somehow we get a distribution of the hidden variables, but then we must prepare some kind of things, that objects that can be measured by our measurements, and the complete probabilities obtained by measuring the measurement MA here. So this is measurement on contextual hidden variable model. And the third idea that we can get here is, well, we can do both of the things at the same time. So only quantum access to preparation and only quantum access to measurement. And this is what's referred to in literature as Specken's contextuality. Okay, in the original papers by Speckens, there's also some other requirements, but this in principle captures the main idea, is that we have only quantum access to the preparation, only quantum access to measurement, and we still ask whether we can find the hidden variable model in the middle. And so now here we get that both of the expressions in the formula are replaced by traces. So what happens is that we get some kind of preparation, rho X. We can apply this n lambda, which is something like a POBM, but negative eigenvalues are allowed as long as this trace n lambda rho X is always positive. And then we have to prepare some object sigma lambda, which negative eigenvalues are allowed as long as this trace sigma lambda MA is always positive. We measure MA and we must get the correct prediction. This somehow means that even if somebody prepares the density matrix and quantum density matrix and wants to measure the quantum POBM, we can still map it in the middle to a classical hidden variable theory. While this might seem somehow inconsequential that there's a quantum preparation, then we go to classical, back to quantum, and then we go then we do a quantum measurement. This would, for example, gives us a perfect eavesdropping strategy, because if you can map the quantum density matrix to a classical system, you can make a copy of the classical system, map it back, have the other party measure, but you still have a perfect copy of what's going on. So somehow this preparation measurement on contextual hidden variable model is the strongest of all of them. And also obviously it's strongest because we require the most. Okay, so by now we have like 5 different concepts of classicality. There were the 2 compatibilities, and there's the 3 hidden variable models. And so now we have a lot of them, and now we want to start reducing the amount. And we can do this by actually proving that some of these things are the same stuff, essentially. So, and for this, there's the first proposition that this EK compatibility. So this is the compatibility where we allow for negative eigenvalues as long as all of the trace expressions are positive. This is the same as preparation on contextuality. So preparation on contextuality was this one where we have quantum access to the density matrix. And here you can see why this is the same as this EK compatibility, because somehow this means that from this pseudo POBM n lambda, which can have negative eigenvalues as long as all trace expressions are positive, from this you can compute any, from this you can post-process any POBM you can measure. And the experts in incompatibility, they know that if you can post-process all of your POBMs from a single POBM, then they're compatible. And this is the idea here, that this is how we can get this proposition that this EK compatibility is the same as preparation non-contextuality. Moreover, we can get some kind of hierarchy between these notions, because one can easily show that this incompatibility of all measurements implies simplex embeddability. Simplex embeddability is this first non-contextual hidden variable model, but simplex embeddability implies EK compatibility. So somehow we can see that this EK compatibility is the same as preparation non-contextuality, and there's a hierarchy between incompatibility, simplex embeddability, and EK compatibility. So there's a reasonable, I would say, hierarchy between all of these notions of classicality, and we can somehow say that, okay, which one do we need for which experiment, or which level of classicality do we need to perform something, to be certain that something is happening quantumly in our experiment. Good. So in principle, one can prove some corollaries out of this. One can prove maybe a few more propositions, but this is the main stake, that we can somehow we can order these levels on non-classicality. And now what we want to do is that we want to find some interesting application. And the interesting application I found in the paper is steering. So I don't know how many people actually know about steering, but sometimes I think that everybody must know about steering. Sometimes it feels that nobody knows about steering. But it's in principle very important, because if you ever heard of semi-device independent protocols, where you have something like cryptographic protocol, but you only trust the devices you have in one lab and you completely don't trust the other person, then this is steering essentially. If you don't trust both of the devices, this is non-locality, but if you trust at least one guy, then this is steering. So this is what's called semi-device independent cryptography. Semi-device independent because you don't trust one. It's independent of what one of the devices does, in the sense that you don't trust it. Okay, but here's the main idea. Now our row AB will be a bipartite state, which means it's a state on two different Hilbert spaces. Okay, so then again, imagine like a singlet projector or maximally entangled state, or entangled state of two Hilbert spaces, or it could be separable in principle, but interesting stuff happens only if it's entangled. And one of the Hilbert spaces is usually called Alice, the other one is called Bob. And in our scenario, Alice will measure, and she has some kind of set of POVMs. Now, this A, it runs through the POVM, so sum over A is equal to 1, but this X tells you which POVM, okay? So that's why this X is now behind the line, because it tells you which POVM. And after Alice measures, we get this, what we call the post-measurement assemblage, which is basically that, okay, how do we describe the thing that Alice measures? Well, we perform a partial trace over the A system over the POVM, which this expression describes the thing where Alice measures, obtains the probability, and Bob still has some kind of state that's filtered after what happens when Alice measures. So somehow this is generalization of a Born rule, where only one party measures and the other party does nothing and just keeps their state in their lab. And then what happens is that based on the choice of measurement X by Alice and based on her outcome, Bob's state is going to change. Of course, this changes in a non-signaling way. So Alice has to tell to Bob what's the X, what's the A, and then Bob knows that he has this sigma A given by X. But in principle, we know what will be the post-measurement state on Bob's side. It will be this sigma of X. And we say that there is a local hidden state model for this, if we can express it in this form, which means that for all A's and for all X, there's some kind of classical post-processing of, this is a classical post-processing of only a single distribution over states, which means that here what we have here, the sigma A of X is something like conditional distribution over quantum states. And we say that this has local hidden state model if we can show that this is a post-processing of a single distribution over quantum states. Anyways, we can also take this as a mathematical expression, and this somehow characterizes classicality in this scenario. So for example, if a local hidden state model exists, then this state row AB could be separable, or the measurements performed by Alice can be compatible. But interesting thing is, if the local hidden state model does not exist, then we call this steering, and then we know that the state is entangled and the measurements are incompatible. So for example, if somebody comes to you and say like, hey, I have incompatible measurements and I can prepare entangled states, you say like, oh yeah, send me 1/2 of the entangled state, perform your incompatible measurements. I will perform tomography. I will obtain this assemblage sigma A given X, and then I can actually check if this has or does not have a local hidden state model. And if it does not have local hidden state model, then I can trust the other party that they in fact can prepare entangled states and have incompatible measurements. without ever going to their lab and without trusting what they do. This just certifies it without trusting, like you don't have to trust what they do. You just trust what you do, and this certifies what they, which is the semi-device independent idea. Anyways, checking whether some assemblage has local hidden state model is an SDP. So this is efficient. So this is easy to check on a computer in principle, and that's why people. That's one of the reasons why people use this quite often. Okay, so now we have a sixth notion of classicality, and now we want to show that this in principle has something to do with some of the other notions of classicality we had before. And so what we can do is that we have to construct a restricted scenario because we have formulated everything in terms of restricted scenarios, and we do it as follows. In our steering scenarios, Alice was the one to perform the measurements, but now we will somehow do first stuff with Bob. Okay, so we will construct this steering ellipsoid, which is like the states that Bob can remotely prepare. So now, while Alice is the one performing the measurements in the steering experiments, now Bob is going to do something first. And what will Bob do is that Bob will construct this restricted set K row, which is all possible states that he can remotely prepare, which means that if Bob applies some POVM, then they can post-select on Bob's outcome, and this is some kind of remote preparation for Alice. This K row is the convex set of all possible remote preparations that Bob can do for Alice. And this somehow characterizes like how, this somehow tells us something about the quantum state row and what Alice can see after when Bob is performing tomography somehow, because in principle steering is a non-local experiment, so Alice does not have to measure first, but Bob can like measure first and then Alice measures, and this would still work because they don't, there's no fixed causal order between what they do. And so this is the, we somehow assume that Bob measures first and then Alice only see this restricted set K row. And we're going to restrict the measurement set EM, which is going to be the convex hull and post-processing hull of all of the measurements that Alice can perform. And in this sense, we get a restricted sub-theory of Alice's theory, where the preparations are what Bob can remotely prepare for her using this bipartite state row AB that they share, and the measurements are the ones that she has for the steering experiment. Okay, and now we can prove this theorem that the state row AB is not steerable by the given measurements if and only if there exists a preparation non-contextual hidden variable model for this restricted theory, given a requirement that this row AB is KB full dimensional, which means that it satisfies some mathematical constraint. But in principle, this is quite interesting because here we can show that the steerability of a state by measurements is some form of non-contextuality and corresponds to some preparation non-contextuality for this restricted sub-theory on Alice's side. Which is quite cool because, for example, from this, you can, using the results before, for example, we know that this preparation on contextuality, that's the same as the EK compatibility, where we allow the joint measurement to have the negative eigenvalues. But as I said, this is weaker than E-compatibility, which is where the joint measurement is POVM. So for example, from this, you can immediately get that if Alice's measurements are jointly measurable, then there is no steering. So in some sense, this result generalizes the idea that Alice needs incompatible measurements for steering, but somehow gets this if and only condition given the restriction, given the requirement on the state. But you have to go to restricted scenarios, and this then becomes preparation non-contextuality or this EK compatibility. Yes, I would like to also mention that while this is the result I proved, there's also a dual thing that you can prove, and that you can then there's a nice paper by Armin Tavakoli and Rope Uola, where they show that measurement compatibility and also assemblage steerability can be the same as measurement non-contextuality, but they use a little bit different settings. Like instead of first doing something on Bob's side, they first do something on Alice's side. So then this preparation on contextuality becomes measurement on contextuality in their paper. But it's somehow it feels like the results could be in some sense dual or connected, but this I don't think if this is known yet. Yes, so with this, I'd like to thank you for your attention, and please feel free to ask any questions.
Thank you, thank you. Very clear presentation. Well, I do have some question. First, if you can go back to the slide of the steering, the first one. So if I understand correctly, what you're saying here is that there are certain density matrices that you can only create by a partial trace. There is no Krauss operator that gives you the density matrix to test if the lab is able to produce entangled state. Is this?
No, because you can always prepare anything locally, or at least we usually assume that you can prepare anything locally from whatever state you are given. But the point here is that you can prepare this where only the raw AB is the shared resource between the two parties, you know, because somehow by doing some stuff on one party you are influencing the other party. So then, like, you cannot just apply cross operators on the other party. You have to work here and to influence something over there.
Mm-hmm.
In some very generalized sense, you can. This is slightly similar to the idea of phase kickback, where you do something on one qubit and this influences the other qubit. This is
okay.
Morally something like that, but okay, mathematically very different, but somehow.
And speaking about things that I can hope to understand, do you think that like what you presented here is related to or can be used as a tool to prove non-dequantization of certain quantum algorithms, maybe?
I think that in principle, yes, because when we had here these hidden variable models, we went the way of asking if we have quantum access only to this and that. But in principle, in quantum computation, there's only single preparation and single measurement, but the interesting stuff happens with the channels or the unitary gates. And there one can ask, okay, if there is some kind of hidden variable model which is efficiently computable based on the gates, and if there is no such thing, then the algorithm should not be quantizable in the current form. But then there's another caveat, is that sometimes these algorithms, like, you only care about part of the output and you can change the rest. And then this is also another caveat, but my hope is that one day I will read a very good paper about this, and that would make me really happy. Because I think while we can write down the definitions, I did not find anything I would be able to prove so far about this.
There's a paper by Noah Linden and Richard Josa about the fact that for exponential speedups you need entanglement or something like that. It's a very old paper, 20 years old.
Yes. Yes, but here it will be a little bit hidden, because somehow, while they assume that the different qubits must become entangled at some point in the computation, right? Here it would all be about the channels, so the entanglement would be replaced by some kind of application of CNOT gates, but this application cannot be trivial, because we know that we can, if we would have just CNOT gates, then we can simulate this classically anyways. So. So there's always these nuances that one would say that, okay, if my algorithm involves CNOT gates, it must be quantum, but then not really. You have to use them at the correct time to create entanglement.
Okay, thank you. I don't know if someone else has questions.
I have. Hi, Martin.
Yes, hi.
Yeah, I was wondering, maybe something similar could be do with channels, because I'm not entirely sure what. Of course, the compatibility part in this POVM case kind of could be also be viewed for channels, and I think you also have some paper on like channel steering with channels. So maybe there's something
Yes.
similar that could be done in this. I'm not sure.
I'm not sure as well, because with channels it becomes even more crazy. But yes, in principle, something like this could be done, where one can here in the hidden variable model assume that there's also some kind of channel in the middle going from K to K or from K to something else. And then we can assume that, okay, what if we have only quantum access to this channel, whatever that means, or
yeah, probably we can only put we have some restricted inputs for the channels, and we have some restricted measurements on the output to find out what's actually happening in the channel.
Yes.
It becomes a bit messy, I think.
Yes, but I mean, the dream would be to unmess this and have a clear picture of what happens with channels. Then also, one thing I was thinking here is that maybe one can also then include all of the preparations and measurements into the channels. So one would have only one preparation and one measurement, and everything else will be described by different channels, which could simplify the things, because if you have only one preparation and one measurement, then this becomes trivial. But still, I don't have a clear results for this. But I'm really interested in having or in doing something about this.
Well, I don't know if there are other questions from the audience. And maybe you can say a few words like about what happens if we have only pure states.
If we have only pure states, everything happens almost in the same way, because as I said here at the beginning, we assume the set of preparable states to be something like convex. So we get this convexity for free, which means that from only pure states we get all density matrices. But also, since all of the stuff that we do here is based on linearity and positivity, then it's sufficient to do it only for pure states. So without loss of generality, we can forget about the stuff that's in the middle for checking positivity. And then this would somehow happen in the same way. Maybe one can then simply, like then the question is also, what are the pure states? Because like, if we can prepare only some pure states, then yes, then this would be what you would expect. But also, if we can just prepare strictly smaller set of the density matrices, then the pure states would be not vector states anymore. So, but in principle, it would go the same way. Maybe some expressions could be rewritten just in terms of vectors.
Mm-hmm. Okay, thank you so much.
Yes, thank you for inviting. Thanks for all the good questions. Yes.
I hope to see you soon in Singapore, and thanks everyone for coming. And I will say also to Martin, see you Friday.
Yes, see you on Friday.
Thanks everyone.
Thank you.